then I will start. Congratulations to Bikasinam for having such a big event. I had long interactions with him for over 40 years. I remember him very clearly when he visited me in Japan for the first time in the 1980s. At that time, I was at the University of Tokyo. He was also young. Today, I'd like to present the J-power today and tomorrow in nuclear and particle physics. In particular, the neutrino experiment first, and then in the nuclear physics infinity implantation nuclei with proton, pion, and kaon beams. And then the third, heavy ion acceleration at the J-power. Perhaps the audience may not know about the J-power procedure. This is located about 100 kilometers north of Tokyo, and it started operation in 2009. Construction started in 2001. This facility consists of 400 MeV dynams followed by 3 GeV synchrotron followed by 30 GeV synchrotron. Can be up to 14 GeV. Currently we are running for 30 GeV. And from 3 GeV, the material science and life science, the experimental facility there. And from 30 GeV, we have an atom beam facility and the neutrino beam facility. Now, before the J-power construction, some of the large conference was held at the KK workshop, and the Bikasinam is here, and this is me. After the completion of the J-power, the first ANFA, Asian Nuclear Physics Association workshop was held at the Tokai, where J-power is located, and there is a big machine. Perhaps the audience, okay, if a proton beam hits the nucleus, pions or kaons or neutrons are created, and the pion decays into muons and neutrinos. At the J-power, 4 muon beam channels and the 22 neutron beam lines exist to study material and life science at the 3 GeV. And we use pion beam, neutrino beam, kaon beam, and proton beams for the study of particle and nuclear physics. And today's talk is focused on particle and nuclear physics. First experiment is a neutrino experiment. The neutrino beam is coming somewhere here. From pion beam, muon neutrino will be created. Both mu and mu and mu electron neutrino and muon neutrino are detected at 300 kilometers at the distance of the Kamioka, where super Kamiokande neutrino detector exists. This is why the Tokai, where the park located, and the Kamioka cave, and this experiment is called P2K experiment. The first experiment measured the disappearance of a mu, which was already measured before, but the very high statistics data were obtained at the J-power to decide neutral mass difference in 2021 to 0.050 plus minus 0.008 electron volt. In the second, the appearance of a neutrino, electron neutrino, was measured to determine theta-1,3, the mixing angle between the first and the third neutrino. This parameter was not known before this P2K experiment. This is the first data from P2K published in 2011 in Nature, discovered letters, immediately after the data operation. The mixing angle of theta 1, 3 was determined to sine square theta 1, 3 to about 0.1. Namely, theta 1, 3 is a 0.16. The mixing angle theta 1, 2, 1, 3. However, in this experiment, mu decays into mu and mu tau, and 5% run is detected, not direct measurement. And there are strong influence from the imaginary part of the matrix element between mu E and mu tau, where we want to measure. That is related to CP violation. This part induces a wavy structure of sine theta 1, 3, namely shown here. In 2012, immediately after the publication of P2K result, a reactor experiment on the disappearance of electron neutrinos to tau neutrino was published. In this reactor experiment, theta 1, 3 was able to measure directly with much higher statistics than P2K. These results are shown here, first in a Diabei experiment here, and soon after, Reno experiment in Korea published the result. These results are shown in this blue line here. Those days, however, P2K people thought deeply that if the statistics were increased higher, it might be possible to measure delta CP, the CP parameter for the neutrino sector, by observing the crossing point between the two. Namely, if this crossing point is correct, this is close to minus pi over 2, the maximum CP violation point in the neutrino sector. At this point, let me comment on the CP violation. Lee and Yang predicted that the parity is 100% broken in a weak decay, such as beta decay. Then CS2 proved it from the polarized cobalt 60 experiment. Namely, neutrino carries left-handed neutrino alone. If the parity operation is applied, this operation introduces the right-handed neutrino, which does not exist. The C operation is a particle anti-particle inversion. If CP operation is applied, the right-handed anti-neutrino shows up and it can exist. This was called CP invariance process. Later, CP violation was discovered by two partners of kaons at the 0.2% in 1964. It was a port-level discovery. However, no one knows if CP violation exists in the lepton sector. Right-handed neutrino might exist because if one observes a finite mass neutrino from a moving frame at the velocity of c, the neutrino must be right-handed because the speed of a neutrino must be smaller than c. The most direct evidence of the CP violation is to compare mu decay to mu e decay, compared as with mu bar decay into mu e lepton neutrino bar. And they succeeded observing this data, although I will skip detail. They succeeded in detecting these, and currently the number of delta CP is about 1.9, which is close to 1.57, which is a maximum CP violation. However, the weakness of this experiment is only at the 3 sigma level and not the 5 sigma level, which is required normally. In Japan, therefore, 2 big projects are now in progress. The first one is to upgrade the super Kamiokande into hyper Kamiokande by increasing 8 to 10 times volume of the detector. The second is to increase the beam intensity at the J-part from 0.5 megawatts the current to 1.3 megawatts. The government officially approved both projects, and they are constructed. However, to complete the entire project, we must wait until 2027. Also, there is a significant competition with a Fermilab Nova experiment, where the similar study is run. The next subject is nuclear physics, particularly impurity implantation in nuclear labs with ions and chaos and proton beams. Proton beams in nuclear physics is particularly in here, and they are extracted here. And inside the hadron hole, the ion beams and the chaos beams are produced. Here I summarize, sorry. Okay. Here I summarize how to study nuclear matter physics. Inside the nucleus, the internuclear distance is about 1.87, which is close to twice the nuclear radius of 1.27. Therefore, the nucleons are fully packed inside the nucleus. The first trial is to implant impurities such as lambda or cascade, K minus, Parkinson in the nucleus to probe the interior of the nuclear matter. These efforts are carried out at the J-part. The second trial is to heat the nucleus up to a very high temperature so that the quarks be confined to form a quark-gluon plasma, which is the main subject here. This area has been studied very extensively at the RIC and the LHC. The third trial is to compress the nucleus into high density. The neutron star already exists in the universe, but the accelerator studies have not been done in so far. At J-part, we are trying in this direction as a future plan. The current activity at the J-part as follows. The first one is to study lambda or cascade in nuclei, which is called hypernuclei. Secondly, implantation N minus inside the nucleus. And the third, low omega fluorescence produced by primary proton beams study. The first example is a lambda implantation in the nucleus. This is called the lambda hypernucleus. The angular momentum from 0, 1, 2, 3, 4 up to 4 has been measured. Also, the depth of the potential is at around 30 MeV. In the normal nuclei, for example, scandium 41 carries the spin and parity of the outer proton alone. Namely, traditional nuclear physics probes the surface of the nucleus alone because observing the inner core is prohibited by the Pauli principle. Due to this feature, the binding energy of a nucleon is approximately 8 MeV, independent of the mass of the nucleus. On the other hand, lambda probes the interior of the nucleus. In addition, therefore, the binding energy of one S8 is close to 30 MeV, which is bigger, much bigger than the nucleon binding energy. In the next, I will discuss the strangeness of -2 hypernucleus. The left figure shows that the mass number dependence of the binding energy up to 14 or 15. The lambda hypernucleus, simple lambda hypernucleus, is binding energy increases linearly against the mass. This is not all because the binding energy for a much heavier mass approaches to 30 MeV. So either mass is only half of the heavier mass binding energy. Similarly, the binding energy of lambda nucleus is about twice of the single lambda hypernucleus here, and it approaches to close to 60 MeV in heavy nuclei. The right figure shows a publication of the last year in 2021 on the cascade hypernucleus. The binding energy is not significant at this nucleus, and the study is in progress. The next subject is a K- implementation in the nucleus. Many people have thought that the K- is quickly absorbed by the nucleus. However, one group discovered that K- could be bound to guide protons here to form a bound nucleus. This was a surprise to us. Of course, this is a finite derivative. According to the theory, if K- were bound, for example, in ppm, the entire nucleus would be shrunk. From this point of view, the study is fascinating in relation to the formation of high-density nuclear matter. Now I come to the last subject of the hadron experiment. Proton-induced meson experiment. Many years ago, Dr. Nambu proposed that the spontaneous symmetry breaking produces a mass of baryon or meson. After that, Matsuda and Weiser proposed a reduction of the mass in the plane of temperature and density. In fact, along the temperature side, the mass becomes zero at a specific temperature. By now, it is known that it's about 556 MeV plus according to the lattice QCD. Here, the core mass was assumed to 0. According to their prediction, if one goes to higher density side, mass would also approach 0. Even at the normal nuclear matter density, the mass would be somewhat reduced. Before JPAC, the KEK group, the KEK group, studied the pi-meson mass inside the nucleus. There was a hint in reducing the mass of the pi-meson atom, as shown in this figure. At the JPAC, extensive studies are in progress to study if the reduction is correct. The data taking is in progress, and unfortunately, I cannot show the data itself, but many people are spending their effort on this experiment. This is Accelerator application alone. This experiment is called the ED16 experiment, and their experimental device is shown here. By using the remaining time, I will discuss the third topic of heavy ion acceleration at the JPAC. This is an observed baryon density in the central region, namely at around 1 cm equals 0. The baryon density is minimum at the Rick energy. At the SPS energies of 200 GeV per neutron on a fixed target, the baryons are still forward and backward free. But the some baryon remains in the mineral peak. Finally, at 80th energies at 50 GeV per neutron on a fixed target, the baryon density is peaked in the mineral peak. The nucleon may stop each other at these beam energies. Now, let me consider a simple relativity. If a rectangular object moves rapidly, the arrival time from point A and point B via light are different by about this 1/c time. During this time, point A moves earlier by